This comprises 6 parallel 10 kilovolts, 10 amp silicon carbide JBS diodes. And series Schottky diodes to bypass the silicon carbide MOSFETs right there. Okay? So this is available today. This was used in some prototypes for solid-state transformers, primarily in the DC to DC converter. Here are some waveforms at 5 kilovolts, 5 kilovolts amplitude, and 100 amps current. And so this is a half-bridge module, and these are the switching waveforms. So, you know, as I said, these are components that exist today, either in prototype form or in laboratory sample form. And here it is. This is a 15 kilovolt, 20 amp, and IGBT, and channel IGBT. So you have here the diodes or the diode components and the IGBTs, current sensor resistors, and a thermistor in this particular module. A lot of the efforts in this area to produce these modules, these experimental modules, are funded by the military organizations in the United States. And I was making a comment to the chairman before the meeting that one change from the military efforts in the past in the United States is that the military always wanted to have something specific, special for the military applications. Not anymore. And so nowadays, we are called as industry partners in the efforts with the military to help companies like Cree to produce components that will be not only useful for the military applications, but also for the industry, because without the consumption of these parts by the industry, manufacturers will have very difficult time to justify the manufacturing of these special components for military applications only, which is politically driven sometimes. And so they understand now the value of uniting these efforts with the industry. So they provide the money, but they ask us from the industry to give them input as to how the components should behave or should be packaged and so on. So this is new, and a lot of the monies that was spent so far for producing these components came from the military. Here are some of the waveforms for the 15,000 volt, 20 amp N-channel IGBT. So you can see turn-on transition was at 11 kilovolts, 5 amps, and turn-off transition at 11 kilovolts and 10 amps. This is a hard switching waveform. Now, this is something very interesting, and we're very excited about this particular device. It's a 20 kilovolt GTO solution. Now, why is such a device, so important? Is because as some of you know, high voltage DC transmission is very important for efficient transmission of power, or even manage of utility power generation. In the United States, the eastern seaboard operates in a different phase, basically, than the western seaboard. So you cannot connect them together because of phase difference. So they have to utilize DC to DC converters for that. And when you talk about distribution of DC, like what's going to happen in Europe, the high voltage DC highway, and so on, so that you have this utility-friendly distribution for renewable energy farms. So people can only take energy from utility. You can put energy back, and you can sell your excess energy that way. So a very interesting concept, and obviously protection becomes paramount. And a circuit breaker to protect DC, especially high voltage, high power DC, is still not existing. So a lot of people, including us in the United States, are after making circuit breakers, static circuit breakers. I know that ABB recently announced they have solved the 100-year-old paradigm or problem of protecting DC, but they are still a hybrid. They're still a hybrid solution. So full fully static solution would be able to be achieved by a 20 kilovolt GTO. So we have test results here of this GTO. Here is the breakdown voltage at close to 20 kilovolts, and here is the current versus the cathode to anode voltage at room temperature. This is a 2 centimeter square chip, 20 kilovolts, and you can see that 100 amps. We have about 10 volts here, but very low voltage drop at 50 amps. This is about constant, but for switching is not very fast. This is not a very fast switch, but the key thing here is the amount of components that you would reduce by having such a component at 20 kilovolts operating, say, on a static circuit breaker. Now, this is really an interesting thing. This is a chip that is developed by Cree here, 9 millimeter by 9 millimeters, which is a 27 kilovolt, 20 amp N-channel IGBT. So, and so this is something that is really exploring. This was financed by the Air Force as well, but it is something that tells you of the capability of silicon carbide today. And these devices exist in lab sample form today, and you can see here the current versus they say here 20 amps. So you have VG at 15 and 20 volts here. 10 volts, 10 amps will give you roughly at 15 volts, I would say 7 volts of VC. So very interesting that this can be achieved. Now, other silicon carbide component devices in the market as engineering samples you can buy today. A 3.3 kilovolt, 1500 amp silicon carbide MOSFET dual in that package here, and this is the standard Infineon package, by the way. I was not enabled to advertise. I don't know advertise actually who is the manufacturer. So if you're interested in having knowing more about this, please see me afterwards. Okay, system benefits. So obviously, you know, we're talking about the production of these high voltage components in silicon carbide, and what I wanted to say before is that is important to understand is if the technologies exist, people know today, people that have been producing these samples or are now producing engineering samples more than labs. Lab samples are the very special ones, but now engineering samples are available all the way to 20 kilovolts GTOs. The thing is that if the demand increases, the availability of the components is going to be much sooner. So one of the tasks that we in the industry have, and we're trying to apply, we're trying to use and help, because companies that produce these that are normally not power conversion equipment manufacturers. Cree certainly is not. So we in the industry are trying to find and help characterize these new components in order to bring solutions with these components that will tell them, well, the market is going to be so many thousands of parts per year. And so they will take that into consideration and invest money so that these components can come to the market much, much faster. So it's a, it's a chicken and the egg thing. Is that, for instance, they say the MOSFET, the D MOSFET in silicon carbide is something that they could mass produce if they had enough investment and they had enough forecast of components to be sold. So what I'm trying to say is it can become reality, and we are all responsible, directly or indirectly, to increase those numbers so that these companies can bring these components to market. Now, what are the system benefits with these high voltage components? Reduction of the number of levels required for a given multi-level inverter using 15 kilovolt silicon carbide devices. One of the things we're going to have by the end of this year, December this year, is a 6.6 kilovolt two-level inverter versus, and so if I would have two-level inverters with 6.5 kilovolt IGBTs that are available today in silicon, I can only achieve 2.4 kilovolt output on my inverter, two-level. And yet, 6.5 kilovolts can only go, well, the cruising frequency, switching frequency of a 6.5 kilovolts IGBT today is 500 hertz. Okay? So if you want to utilize the characteristics that are in the in this specification sheet, you're going to have only 500 hertz. And when you go to 15 kilovolt MOSFETs, you're talking about 10 to 20 kilohertz. So output filters, etc. You know, even though it's two-level, they are not the same as if you're using 6.5 kilovolt IGBTs in silicon. So very important thing. Now, can you imagine a three-level inverter today? You can reach 46 to maybe 5,000 volts depending on your specifications. Output AC with a silicon carbide 15 kilovolts silicon carbide IGBTs, you could reach 13.8 kilovolts. So the same structure that you have today for your three-level NPC, you could reach voltages that are 3 times higher than in silicon. If you have a four-level, you can reach 6.9 kilovolts with no regulation margin on your controller. But with 15 kilovolts, you could reach 20 kilovolts. And a 5-level, 11 kilovolts in silicon, you can reach 30 kilovolts in silicon carbide.